So, okay guys, questions? We're talking about the Schwarzschild solution. Right, Schwarzschild solution to Einstein's field equation, R mu nu is equal to 0. That's Einstein's field equation in vacuum. And the Schwarzschild solution, which we derived, ds squared is minus 2gm over c squared r, here, c dt squared plus minus 2gm over r c squared minus 1. dr squared plus r squared d omega squared. This is the Schwarzschild metric. Then we discuss the singularities, and then we discuss motion of particles. So we saw that in principle we can write down the geodesic equation, but that's not going to get us too far because we end up with 4 equations which are difficult to solve. Instead of that, it's better to write down, use a Killing vectors which you learn, look for conserved quantities, conserved constants of motion, and write down the metric compatibility, epsilon x mu over the lambda. Epsilon is a 1 for massive, 0 for massless, and the photons. And the Killing equation, which we find are 2 constants of motion, so 1 minus 2gm over r dt lambda, the constants of motion which we call E. The second constant of motion is r squared by d lambda, this is L, angular momentum. We have 2 more constants of motion which are associated with the direction of motion. Essentially it tells us that the motion of particles is in a plane. So that sounds. So 2 other constants of motions, 2 constants of motion associated with the fact that theta is pi over 2. Motion of plane. Which is exactly the same result you're familiar with from classical mechanics. This is exactly the current motion. On this equation, we wrote it down as 1/2 dr over d lambda squared plus v of r is 1/2 e squared. V of r is 1/2 epsilon minus epsilon gm of r plus L squared 2r squared minus gm L squared over r cubed. So we reduce the equation of motion into essentially 1 dimension, that is an r. But in the very same way as we analyze the trajectories of particles in the gravitational potential that you were doing in classical mechanics. Again, epsilon is 1 for massive particles, 0 for massless particles, namely photons. And if we remove this part, this is exactly what you get, identical to classical potential, gravitational field. This is how Kepler derived his equation of motion, essentially from here. This term, this is the GR, which of course has an effect for small r's. It changes the sign from positive to negative. That's the dominance. Larger radii this contribution becomes legible. This is a one dimension, but not to forget, what we're really describing is a two-dimensional motion. Well, it's three-dimensional, four-dimensional this time, but it's on a plane. So we have R5 motion, but it's easier to understand what happens here. As we showed, we have two types of trajectories, closed and open. So the source of gravity, let's say sun, for example. And the two types of trajectories we have, the closed trajectories, ellipses, and open trajectories. And again, what this really tells us is R of lambda, right? Remember, I keep on insisting in this course, right? Parameter, a number path, which we call lambda, and then there is R of lambda. This only gives us R of lambda. Of course, we can call for 5 lambda, but that's going to be much easier. Well, not necessarily. We're going to do it today. All right. And then when we analyze the trajectories, we simply plotted this effective potential, right? And this for Newtonian case and for non-Newtonian case. We saw for the Newtonian case, if I plot R, P of R, half. For the Newtonian case, it does something like that. If L is small enough, if L is large enough, it can go like that. And the types of trajectories, of course, we have for the Newtonian case. You have bound trajectories, circle, bound trajectories. Essentially what is plotted here. So you have circle is just a circle. Circular orbit. Bound trajectories between R mean and R max. Mean. This would be R max. Trajectories would be ellipses. The way I plotted it is a little bit misleading because the ellipse is not exact. There's a small motion that small particle returns. It doesn't return exactly to the same point. This precessional motion, which is meaning that the perihelia and aphelia. So perihelia is the point of the closest to the central object, and aphelia is the point which is further away. They're slightly moving and they have their own motion. It's called a precession. Now, in principle, this is something which you're supposed to learn in second year's mechanics course, but I understand that you have not learned it. Right? So in the molecular tutorial, make sure that you're familiar with this classical. It's easy to derive from the inertial tensor. See that? Angular momentum, L is I plus omega. We'll make sure that you're familiar with that. This classically, this is something that you're supposed to know. It's part of what's called a rigid body motion. It's the same thing that you have when you have dreidel, swivelim, when you play with them. Then it's like you're saying that the swivon, right? It's not exactly, it's rotating, right? But when it's rotating, this is making a, it's not just it's rotation. And this one is also making like this. This is also moving like that. So in this shape, right? It's exactly the same. That's called a precession. There's the main rotation, and there is this rotation of the axis itself, which is not exact. Yeah.
Starting this year, we do study.
You do study that?
Yeah.
So who studied that?
With Ilya.
What? You did? So you know what I'm talking about. And the rest, you don't study that. But that's good. But ask me. I don't know why it was omitted from the last years. It's the same thing. Right? It's the same thing. This is actually easier to understand because here you have the torque which comes from the point here. This is the torque here is slightly different. It's a torque. You'll see that also you can see that also in motion rotational curves. People have noticed that. People have noticed this motion from rotation of Earth already in the ancient Greeks, more than 2,000 years ago. They noticed and we calculate. And physically, it's we can look at it. It's not that difficult. For me, it was a standard thing that you learn in second year mechanics. I don't know why it was omitted. I'm glad that they resigned it here. Anyway, so you have this precessional motion. And of course, you have trajectories. This is of course bounded trajectories between R and R max. There's unbound trajectories. Go something like that and then come back. These are unbound trajectories that only have minimum radius. Of course, would correspond here to the point of closest approach. Or so this is the classical straight line, and it will be affected by gravity, and then away the straight line. So think of meteorites. Okay, this is for the Newtonian case. For the GR case, so this is purely Newtonian. For the GR case, full GR, we have a slightly different, actually not slightly, substantially different behavior. Because of this extra term here, then the potential would go to 0 at R equal to Gn over C squared. Asymptotically, it will still approach half. R goes to infinity. And the way it behaves depends on L. Either go, if L is small, one could either go like that. And if L is large, it would go something that looks similar to this. So again, we have two types of bound orbits. One here. Of course, this one is stable and this one is unstable. Didn't have that before. And of course, we also have bound orbits, same type that we had previously, between R min and R max. Will be very similar to what we just drew. But we also have to add up now this unstable orbit. So we do something like that. Again, this is unstable, which means every small perturbation will take it away, spiraling either inward or outward. And also for the unbound orbits, you have trajectories that go and turn, but you also have trajectories that would just get the same as the trajectories we had previously. We now also have trajectories that would go and simply spiral inward and fall inward. And then I pointed out, which is something which is very important observationally, we can calculate where are these points, okay, simply by looking at the VDR equal to 0. And we get that these points are at RC, which is L squared plus minus square root to the 4 minus 12 G squared M squared L squared over 2GM. So they depend on L, the orbital angular momentum. And in the limit where L goes to infinity, so very large L, this would correspond to RC is L squared over GM, 3GM. So very large angular momentum, this is going to be 3GM. And that point here is going to be L squared over GM. Here's going to be 3GM. Now just to get clarified, right? That means that there is a circular orbit, 3GM. Now we're talking about geodesics, namely particles that there is nothing, no forces that act. Nothing prevents a particle from getting inward, right? Less than 3GM, as long as it does not cross this 2GM horizon. It can always come back. It's just not going to be stable. I mean, it's also not stable. Right? It will not stay there radially. Right? But it can happen. And in the limit where L is square root of 12 GM, then these two solutions coincide. We get one solution, which is RC is called R ISCO, which is 6 GM. As I said, this is something which has an important observational consequence from an astrophysics point of view, because what happens in reality is that when there's accretion disk, the inner parts lose angular momentum to the outer parts, so that's why the gas accretes. Accreting, it heats. As it heats, it emits radiation, mainly in X-rays. And X-rays and the maximum radiation will be around here. Right. Below that, there will still be gas, but it will just spiral inwards. Right. So the emission will be much less. So we actually see this, can infer this from the gas. And this is something which is not new. This is known for 30 years at least, likely even more. Through X-ray telescopes, people can infer where the ISCO is. And since the ISCO is linearly dependent on the mass, in principle one can infer the mass of the central object, the black hole, in this case. And in recent years, the technology has advanced such that you can also infer if the black hole is rotating, and then the metric is slightly different. If you have another independent way of measuring the black hole, which often you have if you have binary systems. Right, that was a quick. Any questions about any of that? for completeness, before we move on, what happens to massless particles? So if we're talking about massless particles, this was for massive particles. For massless particles, it's actually very easy, right? We have
Just ask.
right? So for massless particles, so that means epsilon is equal to 0. This we don't care. In the Newtonian limit, right, what do we have? 1, 3, 4. What do we have in the Newtonian limit?
Goes like 1 over r squared.
Right, this is the only term that exists. Right? This is the GR term, and these two don't exist. It just goes L squared over 2r squared. L equal to 1. They all asymptote to the same thing. What happens with trajectory?
Like fraction of flight.
That's right.
It's fraction of flight, but like constant.
No, don't get confused. This is the Newtonian case. Right. So what we're saying is that the radius gets smaller. This only shows the radius, right? Radius gets smaller and smaller until you reach the minimum, and then the radius increases. But what, this is reality, right? What happens if you have to plot the trajectory in 2D? This is the source of,
So way to line.
What?
Lines
right, 2D just goes in straight lines, right? In Newtonian case, light is not deflected by gravity, right? It just moves in straight lines. So what is plotted here? So simply r is a function of lambda. So this is r of lambda. First r goes down, This is r mean. So this corresponds to the point here. And then r starts increasing. It's obvious for everyone. So lambda equal 1, lambda equal 2, lambda equal 3, lambda equal 4, whichever way. This is quite straightforward. Just don't get confused when you're seeing this type of plot. This really corresponds to what happens there. Right? So, you can think of it as the photon is slowing down. What does it mean it's slowing down? That r as a function of lambda goes slow. Of course, it doesn't slow down in the sense that the speed of light is c and the photon still stays the speed of light. But slowing down in the sense that dr d lambda is smaller than 0. Photon still continues to propagate at the speed of light. Okay, so that's quite straightforward. What happens in GR? So again, in GR, now we have these two terms. So again, of course, where r goes to infinity, we don't care. But where r is equal exactly 2gm over c squared. What happened to the potential?
What's that?
Or this is zero.
Zero. Right, it's exactly zero. So if I have to plot the potential, something. So this is unless L is equal to 0. What is L equal to 0?
And it's just like minus.
The photon is just pointing straight forward into the central object. This is the L equal to 0 here. Otherwise, if L is not 0, then there is always some barrier. Like this there. If we have a photon that is going from infinity, reaching the barrier, and then going back. What's the trajectory of the photon going to be?
Yeah, again, the lack of the trick going minimum.
How is that different than the Newtonian case?
Your straight line is different.
What?
Your straight line is on the geodesic. It's not
Right.
Talk
So
about
the
space.
photon trajectory will be tilted, right? So the photon trajectory will go from infinity, and then it will go like that, and then it will continue to infinity. Right. And again, this is R. It's a function of lambda. This is R mean. Now we also have an addition. What is that?
stable orbit. I mean, it's an orbit.
It's an orbit, right? What type of orbit is that?
Unstable.
It's unstable, and this is a circular orbit, which is a RC. And again, we can play the same game that we had before, asking, okay, dv over the R is equal to 0. There is V. So we don't care about the absolute terms. So we have minus L squared RC plus 3gm L squared is equal to 0, which means that RC is 3gm. So this is true for every L, so this part is already misleading. RT is 3gm, which is true for every L. photon trajectory, it's going to look something like that. But of course, this is unstable. So this is 3 GM. Which means that every perturbation will kick the photon away, either inward, either it might spiral inward, or it might spiral outward. That's the true meaning of that.
This is the image that we see on the simulation.
Yeah, simulations. There are claims that we may be even able to detect that in reality, though the chances are not very high because it's unstable. But yeah. And again, the way to understand that, how can it be? Right, so the way to visualize that very easily is to think of this as the potential. So have the potential, and then the space itself is being curved. Very far away, the space is flat. But when you're approaching the 3RG, then the photon will just spiral in. It can either spiral inward or outward. Right, so this picture helps visualizing the Schwarzschild metric. All right, any further questions about that? No? If everything is clear, if I'm going to ask you about that in the exam, you will know for certainty. That's what it is. Please don't eat during the lecture. You can wait until break. Yes? There is actually, okay, before we go, okay, just remind me before we go, I wanted to mention something to you. Okay? At the end of the lecture. Okay, so today this was a continuation and completion of what we did on Sunday, and now I want to move on to a new topic, which is classical tests of GR. So we've been working very hard during the semester to develop all this theory and to show you a little bit of what it means. But remember, at the end of the day, and I think I mentioned that to you at lecture number 1, we are physics department. And physics, doesn't matter what people tell you, is an experimental science. So all the math is very good and very nice, very beautiful if you like it, but it's not relevant unless it gives us something to measure. So this theory would maybe appreciated as a very nice mathematical theory, but in order to be accepted as a physical theory, it has to give us predictions, which can be tested. And specifically, predictions which are different than the Newtonian theory. Right, so today we know of several tests, independent tests of general relativity. So there are what's called the classical tests of GR. Something which are less classical. That's what we're going to do now. Tests of GR. In fact, all the tests of GR, well, nearly all of them. Okay, now what? Before I tell you, I'm throwing the lecture, the question to you. What would be? How would you test general relativity?
We saw the
Eddington experiment.
What?
Eddington experiment of the
What is Eddington experiment?
shift of the light.
Deflection of light. Yes. Right. So we just put right in Newtonian physics, light goes in straight lines. In GR, light is deflected. Right? So this is called deflection of light. Put it as number 2 because there is number 1, which is something which is before that.
Precession of
What?
The what?
precession of the
Precession of the perihelion of the inner planets. This would be number 3, right? Precession of the perihelion of the inner planets. Right. There's another thing which we discussed. Why is it
dilation of time.
What?
Dilation of time. And
Redshift.
dilation.
Redshift. Right. Gravitational redshift. Right, so this is number 1 because this is something which we already discussed. Right? Gravitational redshift. Gravitational redshift. And what other things? There's one which I'm sure that you know, but this is not considered classical. This is something of the last few years. There's another one which is considered classical.
Gravitational waves.
Yeah, this is the one which is the last one. Right, gravitational waves. It's not really considered classical because this is something that, although Einstein himself just aware about gravitational waves, normally I don't teach that in the course of GR. The reason is because gravitational waves is really perturbations. It's a perturbation theory. You take Einstein's field equation and you make like a small perturbation, and then you solve for the perturbation, and you end up with the solution, which is gravitational. So, of course, it's been very high in the news the last 10 years since its discovery. The idea is not new at all. Einstein himself solved that and showed that you can get gravitational waves. The reason why I don't teach it, or typically because we don't have time, and if we have time, I'm adding that, but normally I don't have time, is because conceptually it is not, I mean, it's more mathematical than conceptual. There's nothing conceptual that differs in gravitational waves than in Schwarzschild metric or in the Friedmann-Robertson local metric. So if you get the concept, then to do the perturbation, it's really a mathematical analysis, which takes something like 3 to 4 lectures, and you can derive it. It's mainly on the mathematical thing than the conceptual things here. So that's why I prefer to leave it as a second. But basically, if you understand everything we're saying here, just getting and reading the chapter should be straightforward. Take a few hours and you understand. The first one is the one that I guess you're less familiar with.
The existence of black holes in the first place.
What?
The existence of black holes in the first place.
It's not a classical test. It's a prediction. Right? You can add that because we have seen shadows of black holes. Right? This is again something which is very recent. So it's not something that was there when I was studying general relativity. I guess today you can add it. It's not considered classical. It's something that was studied a long time ago. What else? You may know, may not know.
Time delay.
Which time? What time today?
differences. Like I'm thinking, low self, so the core of the therefore versus something there, I up like satellites away.
Not exactly. It's something that gets closer to the gravitational potential. Right? If that's what you mean, then you're right. It has a name. It's called Shapiro time delay. Yeah. Question?
Wouldn't it be easier to calculate the motion of Mercury?
Well, what's that? Precession of the perihelion of the inner planets. Right? That's exactly it.
Because I would expect to be the first thing they would have done, because they already knew that Newton was wrong about Mercury trajectory.
Right. So, okay, we'll get to that. So, let me just finish. So, this is called the Shapiro time delay. Shapiro time delay. Shapiro is here. Shapiro is still alive, by the way. I know him. I wanted to meet him, but I missed him somehow last 2 weeks ago. So that's following Irving Shapiro. It should be around 90.
What about CMB?
CMB is not related. These are classical tests of general relativity. Yeah.
Why? Well, okay, in that way, why the why the will look on only on the in planets and not all of them.
It's all of them, but of course it's going to be easier to measure it. Right? Measurement is going to be it's extremely small, right? When you're getting away from the gravitational potential, right? When R gets very far away from GM over C squared, right? Of course the effect goes down substantially. Right? So it's simply now in a way you're right, but let's do it one by one. You're right that this was a post-diction of the theory, right? Because there are reliable measurements of the reliable, accurate measurements of the orbit of Mercury, which are there since the middle of the 19th century, right? So Einstein knew, and people who knew that there is some discrepancy between the predictions of the Newtonian theory, and they didn't know why. So there were various suggestions, right? Including maybe there's some extra planet there somewhere. So this is how people discovered planets, if you happen to know. They looked at small perturbations in the orbits of known planets, and they realized that something is missing there. And of course, the reason why it was missing was because there were some extra planets that were there. So there are various suggestions and ideas. Didn't work out. By the way, did you hear of the planet X? The idea of planet X? Are you familiar with that? No? Is there anybody who's not familiar with that? It's a very nice idea. What if there was another planet which was exactly on Earth's orbit, but just the other side of the sun? Never seen. Let's call planet X. People play this. There is no planet. There is no other Earth which is there just half a year away from us. You can show because it's unstable. But the idea was there for a while. So, okay, so these are actually these four, right? This is something which is nice. These are the classical tests which give differences between the general relativity prediction and the classical Newtonian prediction. And they're all independent of each other. We're going to go over them one by one. They're all independent of each other, and all of course, results are fully consistent with the prediction of general relativity, which is why this theory is accepted. So let's go over them one by one. And again, they're all independent of each other. See that? Okay. So what is gravitational redshift? This is something which we already discussed in a way, but we did it in the weak field limit. So now, with the Schwarzschild metric, we have the full. Another thing which I should say, all except the last one are measurements that can be done and were done in the solar neighborhood. This is all something which we do here in our own solar system. We don't need to go too far. Gravitational wave redshift, you can also, as I mentioned it already to you, it can be tested even on Earth. You don't even need to go outside of Earth to see. The rest, we do need to go outside of Earth to see, but we do see. Gravitational redshift, right? So the idea is very, very basic, right? So there is this source, potential. For our case, this is the sun. And we put two observers. Now they are not on geodesics, they are not moving, they are just fixed. So one observer, let's put them here, and the second observer here. Each observer is fixed and has its own location, right? So this would be R1, theta 1, phi 1. and this one is at R2, theta 2, phi 2. Now, if the first observer sends a signal to the second observer, I'm going to tell them something. Right. What is the tau I for the observer 1 or 2, right? Over dt.
One minus v.
1 minus what?
1 minus v divided by.
Right over here. Remember, the tau is the s over c, right? Minus. Right. So I can actually take it straight from here. So this is 1 minus 2 gm over r to the power 1 half. Ri. C is equal to 1. So I can simply take it straight right from here. Now again, this is something that is a little bit confusing here, so pay attention, right? Tau is the proper time. What is t?
T is the time coordinate.
It's the time coordinate. Okay? So this is the way we measure the time. Right? This is the coordinate. Like r is the way we measure the radius. So, observer 1 emits light, which is seen by observer 2, right? So it emits 2 fresnels of light, and the separation is delta t. So delta t, press light, is a 1 minus 2 gm over Ri minus 1 half delta tau 1. Now what happens to delta t between the two observers? Nothing, because they are static. Right? When they measure the same, they use the same time coordinate. Therefore, delta tau 2 is 1 minus 2 gm over R2 to the power 1 half delta t, which is 1 minus 2 gm over R2 divided by 1 minus 2 gm over 1 to the power 1 half delta tau 1. Of course, we don't, when we're looking at light, we don't see the delta t. What do we see? What do we measure? Frequency, right? So frequency is exactly the opposite of that. So omega 2 over omega 1 is frequency of light. Omega 2 over omega 1 is delta tau 1 over delta tau 2, which is 1 minus 2 gm over R1 divided by 1 minus 2 gm over R2 to the power 1. This is the exact result. Remember, we have basically derived that result in the weak field limit. Remember that? Talked about the weak field limit. But this is the exact result. Okay, so now we generalize it. Of course, this is the exact result in the Schwarzschild measure. It's good enough for us. Of course, if we take the limit, in the limit, which limit? R much greater than 2 gm, which is a typical situation. even if we look at light that emitted from the sun, right, the stellar surface, the surface of the sun, right, remember it's something like 5 orders of magnitude greater than 2 gm over c squared of the sun. So this is already the correct limit. And what do we get? You know how to do Taylor expansion of square root? I mean, I shouldn't ask you that, right? But the reason why I ask is because I realize that many things that are supposed to know from kindergarten, many students don't know. So if you don't know, don't feel ashamed of not knowing. Just feel ashamed of not knowing and not saying that. Nobody's going to hurt you if you don't know something. If you don't know and you don't ask them, you're stupid. Okay, so what happens in this limit? Omega 2 over omega 1 is equal to what?
1 minus 1.
Minus GM.
1 is GM over R1 plus GM over R2. Right? Or if you want, this is 1 plus Y1 minus Y2. This is gravitational potential. Right? So as the frequency, so as the phi increases, right? As gravitational potential increases, what happens with frequency? Goes down. Right? So essentially, what happens? We're climbing away from the potential wall, and the frequency becomes more and more red. Again, as I said, this is not to be confused with cosmological redshift. We will learn soon. It's a completely separate phenomenon. Right? Of course, this is consistent. Another way of thinking of it, right, is that when you are sitting in a gravitational field, right, in the Schwarzschild potential, then the time depends on the position where you are. Right? There was a movie about that, I think, a few years ago. I don't even remember the name. I mean, in other words, so what it means that the clocks of two observers, which sit in different locations in Schwarzschild potential, ticks in a different different pace. Right? Bingo. More questions? No?
Now, are we gonna generalize it to every metric?
Of course, this is the program.
No, you said we are gonna generalize it.
What we generalized was for the weak field limit. This is the complete Schwarzschild metric. What I derive is for this Schwarzschild metric. This is something which you measure. So this Schwarzschild metric provides the correct metric that describes gravitational potential of the sun, also of the Earth, on a smaller scale, of course. And this effect, again, this is a completely general relativistic effect. Don't have that in Newton. Okay. In the weak field limit, we just use that approximation. Now we're doing, this is the correct formula, which is true for every radius, not just for that limit. Right? Now you can see where it comes from. Okay, that answers the question?
Yes.
Well, so this is for the rotational redshift. What about deflection of light?
The what?
Deflection of light. What is that again?
It's when light goes near a planet but not near a mass, but not too close where it passes by but gets bent by its gravitational well.
That is true. So you may know that. So let's think about deflection of light. So this is the source of gravitational potential, and we have a light ray. So in Newtonian physics, this light ray just moves on. Right? In GR, the light ray is deflected by the gravitational potential. Now, you may know that when did Einstein become a hero?
When on the sun eclipse,
What does it mean a solar eclipse?
they saw light bending.
Or a day? Know the story? Or a day?
1990.
Why? It was 1919, that's correct. And what is the... Okay, so why do we need a solar eclipse?
Because when there's a solar eclipse, the sun is still in the skies, deflecting, changing the ways the light goes. So if we take a photo of the stars when the sun is still in the skies, when it's night, the stars supposed to be in a different location.
Yeah. So what did you do? What do you do? You want to measure it?
In the solar eclipse, they saw the light bending to the
How do you see it in solar eclipse?
when they
So,
were exactly in front of the sun.
They want something to like cover the sun so we can see what.
Okay, you're missing one thing.
Okay.
So what did they really do there?
You want to, what you want is that you can't actually see stars during the day because the sun is too bright. So
Right.
you want to see the stars while the sun is up, and then look at the same stars when you're on the other side of the planet,
Exactly. What
and
do you
then
answer?
at nighttime, and then you could actually.
No.
Hmm?
No. We are here, right? This is Earth and this is the sun. Right? So during the day, the sun is on top of our head, right? During the night,
Facing away.
we're facing this direction. So it's gonna be helpful for us? Not directly. What did they really do? Yeah?
They saw the stars, I guess, behind the. Yeah, maybe behind the sun too. I see the one on the left, the one on the right.
Yeah.
They saw, and I guess during the eclipse they.
They couldn't.
The
What did
star
they-
shifted in position
Relative to what?
relative to the sun. Relative to the sun's position in our sky.
This is the sun position.
No, I mean
This
like
is us. This is
yeah.
Earth, right?
When we look up, the
Look up, I'm gonna see the sun.
Yeah.
Cover the sun and I'll see some stars. So how is it gonna help you?
Compare it to the other
Compare it to
the
what?
time where the sun, the earth is on the other side.
Right. Thank you. Right. We are orbiting the sun. How long does it take us to orbit the sun? A year, right? So you go half a year earlier, right? Now you're here. Now you're looking at the night sky, right? And you're seeing these stars. Now at that time there were already plates, so you can actually take a photo, right? And you can see the stars on the plate, right? Then you go half a year. Now you wait half a year, right? After half a year we are here. Now you cannot see the same stars because the sun is too bright, so you're waiting for an eclipse, and then you're taking, after you're covering the sun, then you're taking locations of these stars. Then you can compare the two plates, right? In 1919 there are already photos plates.
But wouldn't the moon's position attribute to the deflection, or is it negligible compared to the
I
sun?
don't care. Just want to cover the sun because it's too bright, so you can see us. Right in this way. So that's what we really did. The way we did it was Arthur Eddington, which you may know the name, the famous astronomer, famous astronomer. It is in 1990. Now the question is, what do we expect the bending to be? So we have that. Let's write down back the equation. So you understand what happened? So the first they did it half a year, and then they waited half a year. Right? They had to wait half a year. Otherwise, there's nothing to compare it to. They had to go to locations which we could see the solar eclipse. So they had two locations. One was in Africa, one was in South America. And they nearly missed it. But eventually they managed, because there were clouds. But eventually they managed to write it down. Eventually managed to take a measurement, and then they could compare it. Now I finished to erase it, so let me write it back again. So we had the equation of motion was 1/2 dr over d lambda squared plus v of r equal 1/2 v squared. Where v of r, we wrote this 1/2 epsilon gm r plus l squared over 2r squared minus gm l squared over r. Now we have a light rays which are coming from infinity. So epsilon goes to 0, we don't care. And I'm going to multiply that by 2 and divide by L squared. So I have 1 over L squared dr over d lambda squared. Plus here I have plus multiplied by 2 over L squared. So L squared is gone. 2 is gone, so I have plus 1 over r squared 1 minus 2 gm over r is equal e squared over L squared. Right. So now we're defining a parameter which is called P, the impact factor. B is L over E. And remember that L is r squared d phi over d lambda. So we have 1 over L squared, so it will be d lambda over d phi squared, d r over d lambda squared, so we can write it down as d phi over d r. I'm skipping some algebra here, but you can quite easily fill it in yourself, right? So I'm using that L squared is up here. B is L over E, so I have d phi over dr is plus minus 1 over r squared 1 over b squared minus 1 over r squared minus 2 gm over r. Power 1. So again, maybe I should draw that again better. This is d phi over dr. Yeah. This is the source of gravitational potential. This is the light. Light is going like that, and it's going straight line, and then it's going. Of course, I'm exaggerating, just to get the feeling of what happens. So this is V. This is the impact parameter. Okay, so infinity, I'm taking it parallel to the direction, and I'm seeing how far it is from the central object, right? So b equal to 0 means it goes straight in. Right? This is just different color. This is R, and this is phi. And of course, this would be delta phi deflect. This is the total delta phi. Which in principle you can solve that for given b. That's all. Everything you need. Right? So the only thing you need now is to integrate that from r goes to plus minus infinity. For r equal to infinity to the minimum and then multiply by 2. So what you get is that delta phi is 2 times integral from r1 to infinity. R1 would be the minimum radius. Of what's written here. The r of r squared. B squared minus r squared. Minus 2g of r. Minus 1. Right? This is a turning point. Now, for practical reasons, now this is it's a nasty integral, right? But it's an integral that can be solved. Well, so they give it to a computer, but previously they just solved it. Not sure how. I think you can find it in one of those tables of integrals textbooks. What is the minimum impact parameter that you can have? Practically, now it's a practical question. When you're doing these measurements, right, in 1919, we go back like more than 100 years ago, when they're doing that calculation, estimating what the deflection they're going to see, what is the minimum impact parameter that you can have?
The radius of the sun.
The radius of the sun, right? So that's the minimum one. So you have a b mean, b practically. B must be greater than its lower radius, which is 7 times 10 centimeters, meaning that 2gm over b squared c is smaller than something like 10 to the minus 6. It's a very small. Basically, this means that the deflection has to be very small. Of course, when you go to larger radii, the deflection is going to be smaller. As far as the calculation is concerned, it makes it easier because then you can do some approximations, which I didn't bother doing that. You do a Taylor expansion. If you want, I mark it for myself that you can go to the textbook by Hartel, which is one of the textbooks that I recommended, and it has the full derivation there. So it takes like 2 pages to do the derivation, and you end up that the result is that delta phi. So skipping some parts, the result is that delta phi is pi plus 4g over b, or delta phi deflection delta phi plus pi, which is 4g. That's a very small number. It's something like 1.75 arc seconds. Does anybody know what is arc second? Good.
Here.
Okay. What is arc minute?
60
What?
minutes.
No. Arc minute. angles, right? So I have angles. Right, so how many angles do I have? Yeah, you want to say?
Arc minute is, I do remember exactly the exact metric, but it's basically a measurement of, I guess, angular distance in the sky. So an arc minute will be.
We're all talking about angular distances, right?
Yeah.
So normally when we look at angles, we have various ways, right? But normally we talk about degrees.
Yeah.
Right? We have 90 degrees, 360 degrees. Right? So each degree is very small, right? But each degree I can still divide it into 60, so it's called 60 arc minutes. And each arc minute I can divide into 60, and it is called 60 arc seconds. So it's a measurement of angle. It's a very small.
Yeah, and this is because we cannot linearly map looking up. It's radio.
Doesn't matter. Okay, so it's a very small deflection, but it's still sufficient to be able to see that technology. After it was proved, there are various stories, legends about that one, various measurement errors, etc. Doesn't matter after it was shown to be correct. Einstein, and then people realized what Einstein was saying was correct, and it became popular here. Movie star. All right, so that's the deflection of light. Again, this is something which you should be able. Getting to this equation is very straightforward. This equation, solving it requires a little bit of math, and it's just technical. Okay, that was the second point. Oh, no, it's good time. Wow. Starting to be out of time.
What would be the uncertainty of the photon for this?
Sorry, what?
Like, there is an uncertainty in the of the photon energy, right? Or
I
angle.
don't care about photon. Don't. Here we're just talking about deflection of the light, right?
Yeah, I know.
I'm not talking about the energy of the photons.
I'm asking what would be if there is an uncertainty in finding the photon in a certain angle because of the uncertainty principle, no?
No, you're confusing with something else here. I'm not talking about diffusion. You're talking about diffusion limit. I'm not talking about that. Okay. That depends on the aperture that you have, basically. If you have big enough telescopes, you don't care. If the telescope is small, that's a different thing. Then you have to transform to take a transform of it. But that depends on the optics. Telescopes back then were big enough and good enough to discriminate. Okay, that's about deflection of the light. The third is the precession of the perihelia. So what is the precession of the perihelia?
You described at the beginning where the lines.
First we said it, but conceptually, it's exactly the same thing that we have here. Right? Here we just have deflection of lights. These are unbound orbits. Right? And when we talk about motion of planets, right, then we talk about obviously bound orbits and about massive particles. So it's exactly the same equations. This one is not going to be 0 now, it's going to be 1. Right? And the orbits are bounded. So the math is, so the equation is actually exactly the same thing. Okay, a little bit more complicated, but conceptually it's exactly the same equation, right? You see where it comes from. And about the precession, again, since we understand that many of you have not seen that properly, then there will be a special tutorial about that as soon as possible. And the idea, again, we said that motion is limited in between r mean and r max. Motion of all planets, right, including Earth, all the bound orbits, essentially, by the definition of a bound orbit. And the Earth's motion goes in the ellipsoid, but it's not a perfect ellipsoid. painter. You got the idea? Then I can measure, astronomers measured the perihelion, which is the location of the innermost. I'll just drop the aphelion, the location of the furthermost away point in the orbital trajectory, and it is moving by itself. Yes?
In each rotation, is this perfect in
Only if it's a perfect, if you have a perfect symmetry. In principle, no. Actually, here. No, it can only be perfect if it's when I'm talking about this problem of motion in a gravitational potential. Only perfection you have is if it's exactly circular orbits, namely if R minimum is equal to R maximum. When R minimum is different than R maximum, you must have this precision. You cannot avoid it. We'll show it to you. Actually, I will show it to you sometimes next week. We'll find time. There is no. It just follows down from the equation of motion, essentially from the Keplerian equation of motion. Yeah.
But why does the geodesic cause this recession? I thought it was due to angular momentum.
Well, it is angular momentum associated with the motion of the body. As I said, you have angular momentum, but the vector of angular momentum is not exactly pointing in that, but it's slightly precessive.
Okay.
You'll see that. I mean, it's actually it's straightforward. It's a classical mechanics problem. The difference is this term. Right? People have calculated that way before Einstein. In the 19th century, people knew already very well how to calculate it. Kepler's law was there in the 15th century, right? And people understood the concept of angular momentum since Euler angles. If you study that, this was all well known in the middle of the 19th century. Right? And I mentioned there were good enough measurements of the planets trajectories, right? Starting from the middle of the 19th century. So all these terms were very well known. This term was not known. Right? And that's because of this term, then the planet's trajectories show that the precessional motion was not as predicted. So the precession of the perihelia, so again, Hartel provides the full derivation. Conceptually, it's the same equation, only a little bit more complicated, so I'm not going to write it down. I could, but it will take us another hour to derive it. So I'm just skipping that, and I'm just going to tell you that for small angles, we have the delta phi. So again, this is just the delta phi. This is the addition because of the GR term is going as 6 pi gm over c squared a 1 minus epsilon squared. A, what is A? Go back to Keplerian motion, Keplerian orbits. A would be semi-major axis. And epsilon is
Epsilon is
eccentricity.
eccentricity.
Yes, that's what it meant. Eccentricity. Okay. That is the time that in this course that if you're not fully familiar or you want to refresh your memory about Keplerian motion, this is the right time to do it. Right, because we're talking about how GR effect differs from Keplerian motion. And of course, I mean, needless to say, this is largest for small a. So of course, for all planets, but when a, the semi-major axis, is small, then it's for now, so it's easier to detect. And right, so just for Mercury, the prediction was 43 arc second per century. That's what we're talking about. Tiny bit of a deflection relative to what Newtonian physics would tell us, but it was already known and measured. Of course, consistent. So that's the third point. Shapiro time delay. Shapiro time delay is slightly later. So this was already predicted by Einstein himself. I think it was already post-fiction. Deflection of light, he said this was 1919, was detected. Gravitational redshift was also predicted. I think it was observed, I told you in the 1950s, but possibly before that. This is slightly later, Shapiro time delay. This is here with Shapiro, who is still alive, as I said. And the idea is very simple. Again, you're repeating the same, it's the same thing, only, right, here we solve for essentially d phi over the r, right? What we did here was solving for d phi over the r. So rather than solving for d phi over the r, it's suggested to solve for dt over the r. It's the same thing, but rather than d phi over the r, just saying, okay, let's solve this for dt over the r. For dt over the r, this is the Shapiro. And again, for all orbits inside the gravitational field, and you end up that the t over the r is a plus minus 1 over b, 1 minus 2 gm over r minus 1, and then 1 over b squared minus 1 over r squared, 1 minus 2 gm over r to the power minus 1. What does it mean? It's actually quite similar to what you said, right? So let's say we have a gravitational potential. And we're sending a signal. So we're sending it. So two observers, right? One is sending an observer, one is sending a signal together. Or practically, we can't put two astronauts in very different locations in the solar neighborhood. So what do we do?
Same thing that we did with the redshift at the beginning. We have someone higher up. No?
Not exactly.
Two people just on different, very far away points on Earth.
But we can't really put people at a very far away point from Earth.
No, not from Earth, on Earth. And just
On Earth is too small. Right? Again, this is the difference in time of arrival of signal because the signal needs to arrive close. It's going through close to the gravitational potential, right? This is the difference that you'd have from GR relative to what you'd expect to see from a Newtonian. Yeah.
You put a reflector on the moon, so you
Put a what?
reflector on the moon.
Right. Put a reflector. The moon is too small. So what do? The moon is too close to us to be affected. So we wanted something which was bigger. They simply used Venus as a reflector. So you put a radar signal, you send it to Venus, and then the signal is reflected back from Venus to us. Right? And of course, during the year, right, we are rotating around the sun, and so is Venus. Right? So there are times that we and Venus are at the same side of the sun, and there are times that we and Venus are nearly in opposite sides of the sun. So when we're sending a signal to Venus, it's go being reflected backward. It has to go through the very close to the source of the gravitational potential. So B here is very small.
They
B
use,
is small. That means that the time delay is going to be large. Right?
do they use Venus as a reflector?
Yes, they use Venus as a reflector.
Is it precise enough?
Part yes. So the technology that was they use the inner planets, so either Mercury and Venus. So the axis of time delay for that, we use R1 is equal to B. You have delta T. So when you integrate over that, you have delta T, the axis, right? This is just a GR. Right? It's about 4GM over CQ. It goes as a log of 4R reflector, R earth, divided by R mean, R1 squared plus 1. This is essentially B. It's the closest approach to the center. This is the R. And this is R reflector. This is R. So this is known as Shapiro time delay. The time it takes a signal from Earth to Venus and back is of the order of 1 hour. The accuracy we need is of the order of microseconds. So we talk about something like a 7 orders of magnitude at least difference. And I have the result of the experiment, which is shown here, and you can find this is taken from. This is from the measurement was done in 1970, which is the technology was already mature there, and you can see as a function of the year. Right, this is the time scale here is of a year. So that's the time we and Venus cross orbit, and you can see that the data matches quite nicely. Theoretical prediction. Okay. So again, independent measure. These are all the facts that has. How am I also time? Right. These are all the facts that give you different predictions between GR and Newtonian. And again, it's a bit of pity that Irving Shapiro never got the Nobel Prize for that, but it's a nice. So if you're already here, I brought you a few presents. So what is that? Right, so this is taken from the internet, of course, from the BBC website. So this is the comparison of what we just talked about, the deflection of light. It's a replica, I guess, of Eddington's initial photoplates, photometric plates. So you're seeing that just took the two plates, one which was taken half a year and then half a year later with the solar eclipse, and you're seeing the deflection. It's the same stars, of course, appearing in the sky, different locations, and the closest they are to the sun, then the bigger the deflection is. Right? So that's the same. You can simply go and Google it. You'll see. Didn't invent it. What is that?
Deep field.
That's called Hubble Deep Field. That was taken with the Hubble Space Telescope. And what do you see?
Computational lensing.
Right. What do we mean computational lensing? You're seeing this elongated. Right. What are these?
That's due to the deflection from what do you call it? From galaxies' big gravitational potentials, dark matter overhead.
So, so essentially, this is another example. You can see from here, right? You can see that this and this. So this is essentially exactly the same thing. It's called gravitational lensing, right? So what are we seeing? So. This is Earth. This is us, the observer. And here you have clusters of galaxies. If you didn't know, then galaxies tend to come in clusters. They don't just randomly distributed in space. They like to be together. You have some massive galaxies. Combined, of course, they provide a stronger gravitational potential. And at the back, even further away, there are other galaxies. What happens to the light from that galaxy? Is bent toward us. Right? And then we go here and bend also. So we may see the same galaxy, the light which is just being bent. Right? You can see it. Now if it was an exact spherical potential, of course you never find it in real life, what will we see?
Just a ray.
See a ring. Right? Same source of light here, we'll call this a ring. This is called Einstein's ring. Okay? So we don't really see the full ring, but you're seeing exactly what you have here. So you have certain galaxies in the center, which produce a strong gravitational potential. And there is a galaxy, this is a reddish galaxy, which is in the back, and the light is being deflected. So we see it as an arc, right? So part of a ring. Right? And essentially, this is the same deflection of light we had before, on of course a much different scale, but physics is exactly the same physics, and calculation, you know exactly how to calculate it. It's exactly the same equations we're using. Cool. That's it? Okay, so this is real. We have a real proof of another example, but they all show the same thing. Okay. It's also the same thing, it's arcs that you're seeing from farther galaxies. It's called lensing, there are micro lensing, but there's no point in talking about it. All right, any questions about what we said today? Still haven't talked about black holes. This is going to happen, don't worry. Before you go, I want to have a message for you all. You're given a set of homework every week, right? And the idea is that you submit the homework. Now, normally, I'm trying to be very flexible. And some of you, and I told you that at week number 1, if you have any difficulty submitting the problem for whatever reason, I would like to encourage you to submit it and not give up. So we normally will give you extra time to do it. But we do ask you to do it on time. And I was told from Akshay that there are some people here that consistently don't submit the homework on time and don't ask in advance. Okay? So if you have any difficulty, any problems, first, my door is open. You're always welcome to come and ask me. I may not have time at the same time, but then you can come later after a few hours or after one day. If you have problems submitting the homework, please do that. Please say that in advance, not afterwards. Not after the deadline is passed. I heard from Akshay that some people are persistently coming to us to extensions after the deadline is over. So please don't do it. Still have like 1 more month for the semester. We're getting to the most exciting part of the semester, as I hope you appreciate, but of course that's everybody's up to you. So please make an effort to do the things on time. If you have something which you don't understand, come and ask, we'll answer. And hope you keep enjoying this course. All right? Have a nice weekend. There will be a new problem set today. And